The purpose of this video is to discuss what's known as the partial derivative. We're going to take the idea of the derivative from calculus 1 and we're going to extend it to functions of more than one variable. So suppose we have a function of a single variable x. From calculus 1, we know that the derivative of f at a point has multiple meanings. For example, we can express it as a limit. I'll look at f prime of 2, say. It represents the slope of the tangent line to the function at x equals 2. It also represents the instantaneous rate of change of f at x equals 2. And we know that we can estimate a derivative at a point using a table or a graph, but we can also compute it exactly using a shortcut. So just as a brief refresher, let's suppose that y equals f of x equals the natural log of x. And let's focus on x equals 2. In black is a graph of the function, f of x. In red is the tangent line at x equals 2. And we can see that the slope of that tangent line is positive. So f prime of 2 is positive. We can estimate f prime of 2 using tables of values. So here's a table of values where x is close to 2. We can estimate f prime of 2 by looking a little bit larger value of x, like 2.1, and we can take the change in outputs divided by the change in inputs. So 1.558 minus 1.386 divided by 2.1 over 2, that's an approximation of the derivative, which simplifies to be 1.72. There are lots of variants on that idea about how you choose points, but this is one of the simplest ways. So an approximation of f prime of 2 would be 1.72. Now I also know that I can calculate f prime of 2 using the product rule, a derivative shortcut. If you go up and compute the derivative of this function using the product rule, and you simplify the result, you will get the natural log of x plus 1. And just to check that, you may want to pause the video for a moment. So using this formula, f prime of 2 is the natural log of 2 plus 1, which is approximately 1.693. So this value is not too far from our estimate, which is both values are positive, which is what we would expect looking at the graph. Now we're going to discuss the idea of what's known as a partial derivative. And for purposes of the discussion, I'm going to focus on a simple function, x squared minus 2y squared plus xy. I've plotted the surface here. I'm going to focus on the point where x is 2 and y is 1. So that point is highlighted in black here. If you take the formula for the function and you substitute 2 in for x, 1 in for y, here you get 4. So that means f of 2, 1 is 4. So the height of this point above the xy plane is in fact 4. Now, through this point, we're going to consider two cross sections. So for one of the cross sections, y is 1. So I'm going to look at the surface and I'm going to fix y at 1 right here. So y is equal to 1. And I'm going to look at what happens as x varies. Now keep in mind, if you look at the axes, as x changes, that's moving in that direction, not that direction. Now, that's a cross-sectional curve. I also want to look at what's happening, say, if I fix 2. So if I fix x at 2, x is fixed at 2, and I'm letting y change. So y is increasing as I move from left to right. Let's suppose I fix y to be 1. I take this formula and I get f of x 1 is x squared plus x minus 2. I just substituted 1 in for y. I know the derivative of this function from calc 1 is 2x plus 1. And if I substitute in, I get f prime of 2, 1, which is 5. Now that makes sense. Let's go back and look at the surface. If we take this curve, and if we lift it off the surface and rearrange it so the positive x-axis, notice how it's coming out like this, goes from left to right. In other words, take this parabola off the surface and rotate it, we would get this curve. And we can see that the slope of the tangent line to this curve is 5. Let's do the same thing where x is fixed. So let's take the curve where x is 2, take it where it's on the surface, lift it up, and plot it as a cross-section. And we can see that it's going to sort of open down like that. If we do so, we get this parabola, which is opening down. If we fix x at 2 and substitute into this formula, we get a cross-section that looks like this. And we know how to compute the derivative of this with respect to y. Derivative of 4 is 0, derivative of 2y is 2, and the derivative of minus 2y squared is 4y. If we substitute 1 in for y, we get negative 2, and that makes sense because the slope of that tangent line is equal to a negative number. So, the partial derivative. In general, suppose that we have a function of two variables. The graph of f is a surface. At a particular point, like 2, 1, we can look at the slope of the tangent line in either the x direction or the y direction. So the partial derivative of f with respect to x at this point, we denote using the notation f sub x 2, 1. It has multiple meanings. It represents the slope of the tangent line to the graph of the surface in the x direction at the point 2, 1. The slope of the tangent line to the cross-section, f of x1 at x equals 2, or also the instantaneous rate of change with respect to x at this point, 2, 1. Now, when we discuss a partial derivative, we always have to say with respect to x or with respect to y. You'll sometimes see a different notation, the partial of z with respect to x. This is a del symbol. It looks sort of like a backward 6, evaluated at 2, 1. This is sort of like in Calculus 1, we might use that notation to represent a derivative. We might use this notation to represent the derivative at 2. So think about f sub x as being analogous to f prime, and think about this notation as being analogous to dy dx. Now the partial derivative of f with respect to y at the point is denoted by f sub y 2, 1. It has multiple meanings. It is the slope of the tangent line to the graph of the surface in the y direction at 2, 1. It is the slope of the tangent line to the cross-section, f of 2y at y equals 1. It is the instantaneous rate of change with respect to x at the point 2, 1. And we can write this using the second notation, the partial of z with respect to y. So notice this is the partial of z with respect to y at 2, 1. This is the partial of z with respect to x at 2, 1. So the partial of f with respect to x at 2, 1 is the slope of the tangent line in the positive x direction at 2, 1. Now it's somewhat hard to see in my illustration, but there is a tangent line drawn in red. That tangent line is at the point 2, 1, and it's where y is fixed at 1 and x is changing. And notice how as x increases, that line has the property that its outputs, its z values, are getting larger as well. The partial of f with respect to y at 2, 1 is the slope of the tangent line in the positive y direction at 2, 1. And we can see, looking at the curve, at this point, so this is the y-axis right here, that as y increases, this line is pointing downwards. It has a negative slope. And so that slope is the partial of f with respect to y at 2, 1. For a function of a single variable, we know that the sign of the derivative tells us something about whether a function is increasing. So for example, if f prime of 3 is increasing, then we know that as x increases from 3, f prime is increasing, and vice versa. Now for the partial derivative, we can do exactly the same thing. The partial of f with respect to x at 2, 1, or the partial of f with respect to y at 2, 1, by looking at the graph of the surface, the contour diagram, or the appropriate cross-section. So look at the point 2, 1. If x increases, If z increases as x increases from 2, then we know this partial with respect to x, 2, 1 is positive. On the other hand, if z decreases as x increases, we know the partial of f with respect to x at 2, 1 is negative. So we can see this different ways. So let's go back to that red tangent line. As x increases from 2, the z values go up. That indicates that the partial of f with respect to x at 2, 1 is positive. We can also see it from the cross section. When y was fixed at 1. As x increases, if we plot the tangent line at x equals 2, we see that has a positive slope. So that's another indicator that the partial derivative with respect to x at 2, 1 has to be positive. But still another indicator is to look at the contour diagram. Here's the point 2, 1. I've labeled my y-axis, I've labeled my x-axis. I've created a contour diagram using Mathematica where the change in z between successive contours is 2.1. So let's look at what's happening at 2.1. Let's say y is fixed at 1 and x increases. If x increases, my z values go up. As x increases, z increases as well. So that suggests that the partial of f with respect to x at 2, 1 is positive. Okay, and we can see that if we look at the contours. And you might want to just pause for a moment. You take a look at the labels, you can see that x is increasing if we move in that direction, 4.2, 8.4, 12 point something. Now let's take a look in the y direction. Let's start at this point and let's let y increase. Now as y increases, take a look at the contours. That's as I move in that direction. Look at the contours and how they're labeled, and you'll see that I'm going downhill on the surface. So that means as y increases, z decreases. So the partial of f with respect to y at 2, 1 is less than 0. So we can ascertain whether a partial derivative is positive or negative by looking at the contour diagram or the surface or the cross section. Now, how do we actually compute partial derivatives? When we are looking at a situation when y is fixed, like 1, in this formula, y is a constant. So what that means is that to compute the partial derivative of f with respect to x, we treat y as if it was a constant, like a 5 or a 7 like that. So in this formula, if we think of y as being a constant, just take the derivative in such a manner. So for example, to be more precise, let's look at this formula. If we take the derivative of x squared, we get 2x. Now look at this term. Normally we might think of the derivative of this as being minus 4y, but we're treating y as a constant. And if y is a constant, this whole thing would be a constant, so its derivative would be 0. Now take a look at this. We're taking the derivative with respect to x. If y was 3, this would be 3x, and the derivative would be 3. If y was 7, this would be 7x, and the derivative is 7. In general, if we treat y as a constant, the derivative of yx with respect to x would be just y. So that is a formula for the partial of f with respect to x at xy. And if we substitute 2, 1 in, we get 5, which makes sense and agrees with what we got earlier. Now let's say we want to compute the partial of f with respect to y. We do exactly the opposite. We treat x as if it was a constant. Normally, if we took the derivative of this, it would be just 2x, but if we're treating x as a constant, the derivative of a constant is 0, so that would just go away. If we treat y as our variable now, and take the derivative of this, we get minus 4y. Now, treat x as a constant. If x were 5, The derivative of 5y would be 5. If x is 7, the derivative of 7y would be 7. And so in general, the derivative of xy with respect to y is x. If we substitute the point 2, 1 into this formula, we get that the partial of f with respect to y at 2, 1 is negative 2. So calculating derivatives, partial derivatives, is easy so long as you keep in mind that one of the variables, either x or y, you're going to be treating as constant. Here's what I would like for you to do in preparation for class. Compute each of the specified partial derivatives. For each one, write a sentence explaining what your value represents in terms of the slope of a tangent line to the surface. Write another sentence explaining what your value represents in terms of cross-section slope and what your value represents in terms of instantaneous rate of change. So here's the first function. I would like for you to compute the partial with respect to x and the partial with respect to y using the shortcut method I showed you on the previous page. Then compute the partial with respect to x at 2, 3 and state what it represents in terms of tangent slope. Be clear and thorough. Do the same thing using this function, computing the partials with respect to x and partial with respect to y. Then compute the partial with respect to y at 3, 0 and state what the quantity represents in terms of tangent line slope. Be clear and thorough. So what you might want to do, whoopsie, not that slide. What you might want to do is go back, and when you explain what your value represents in terms of slope, you might want to follow the template that I've been using right here. So that's it for partial derivatives.